Hello everyone, welcome to the course Nature and Properties of Materials. In week 1, we'll talk about Introduction to Engineering Materials and Mechanical Properties. So this course is offered by Professor Bishak Bhattacharya from Department of Mechanical Engineering, IIT Kanpur, and I'm your TA, Alka Jangid from IIT Kanpur. So firstly, we'll be going through some sample assignment questions which will be helping you in solving your weekly assignments. And then we'll go through some lecture notes. So first question is, in a standard tensile test near the elastic limit zone, then you have to fill in the blank. So your options are tensile stress increases in linear proportion to the stress. And second option is tensile stress increases at a faster rate and tensile stress decreases at a faster rate, or none of the mentioned. So the correct answer here will be third one. Okay, so for answering these type of questions, you should firstly remember the stress strain curve for a particular material. Okay, so initially it will show this Hooke's law where it will be linear increase in the stress with the strain. Then there will be strain hardening region where here plastic deformation is taking place. So here the stress doesn't increase faster but decreases slower. Then in necking region it starts decreasing. Okay, so here tensile stress decreases at a faster rate will be the correct statement. So during tensile testing, if the material is stressed beyond the elastic limit, the tensile strain increases faster as compared to the stress. Now next question is, what do the two subscripts of stress tensor represent? Your options are directions of stress and strain, directions of strain and normal to the surface on which they are acting, or directions of stress and normal to the surface on which they are acting, or direction of the stress and the flow direction. So in case of stress, you should remember it will be one of the direction of stress and normal to the surface. So third one will be the correct statement. So you can also visualize and see how these subscripts work. Okay, so someone has joined. Okay, so for those who have joined late, so we are going through some sample assignment questions which will be helping you in solving your weekly assignments. Okay, so first question was, in standard tensile test near the elastic limit zone. So your options are tensile stress increases in linear proportion to the stress, or tensile stress increases at a faster rate, or tensile stress decreases at a faster rate, or none of the mentioned. So in this region, you have to, near the elastic limit zone, the tensile stress decreases at a faster rate. So initially it increases, then it increases at a slower rate, then it decreases at a slower rate. Then you have to, second question is, what do the two subscripts of stress tensor represent? So in case of stress, you have to remember it will be denoting direction of the stress, not the strain. So one of these three can be correct, and other option it will be normal to the surface. Okay, so these two questions can be correct because in other two there is strain mentioned. Okay, so third one will be correct because other subscript will represent normal to the surface. Okay, so this is this is the sample, few type of sample, then these are the various stress tensors that will be acting. So first subscript will be the direction of stress and other subscript will be the surface on which they are acting. Okay, so here it is shown like this is the third surface, then this is 3 3 in 3 direction and in 3 surface. Here it is two direction x2, and also in surface is also in two direction. Next question is, this statement is correct? Your options are necking starts at the yield point. Okay, so as you know, necking starts at the okay, so for those who have joined late, we are going through sample assignment questions. So third question is, which statement is correct? So statements are necking starts at the yield point. So we know that necking starts at the ultimate tensile strength point, UTS point. Okay, so this statement is incorrect. Other is yield point phenomena are seen in aluminum. So yield point phenomena is seen in the materials in which you will be having some interstitial atoms there. Okay, so in case of aluminum, it is a pure metal, so it won't be showing any yield point phenomena. And next is endurance limit can be determined by tensile testing. So endurance limit is tested by fatigue test, not tensile test. And last statement is yield strength is structure sensitive property. So this is correct answer, correct statement. Okay, so yield strength of material changes with microstructure. For example, annealed, normalized and hardened steel of the same composition will show different yield strengths. Okay, so as we see in case of steels, annealed meaning you'll be cooling your sample in furnace, while in case of normalized sample you'll be cooling in air. So it will be cooling faster compared to annealed sample. So it will be having fine microstructure compared to this. In case of hardened steel, you'll be cooling it with some coolant with help of water or other oils. So this cooling rate will be further higher. So it will be showing very fine structure. So depending on these microstructures, you will be seeing change in the yield strength as well. Next is necking starts at ultimate tensile strength point. So as we saw in previous question, so here at this point necking will start. So necking meaning your material will be having uneven cross section. So there will be very smaller cross section forming at a particular width of the sample. And then yield point phenomena are seen in alloys with small amounts of interstitial atoms such as mild steel. And endurance limit can be determined by fatigue testing, while tensile testing gives tensile properties such as elastic modulus, stress and strain, and yield strength, etc. Next question is, what is the ratio of Young's modulus of elasticity to the modulus of rigidity in terms of Poisson's ratio? So your options are 2 times 1 plus mu, 1 plus mu, 2 times 1 minus mu and 1 minus mu. So mu is Poisson's ratio and your Young's modulus is denoted with capital E, and elasticity and modulus of rigidity is with the capital G. So correct answer will be first one. So in your lecture notes also you are told the relation between E and G is capital E equals to 2 times G times 1 plus mu. So if you want to find out the ratio, so E divided by G will be 2 times E plus mu. So you can be asked various numerical based on this as well. So you can be given values of for example elastic modulus and Poisson's ratio, and you can find out shear modulus. Next question is, what is the formula for Rockwell hardness? So a lot of questions are asked based on Rockwell hardness as well. So the correct formula will be second one. So N is N and your H are the constants for particular scale that you are using for measuring Rockwell hardness, and D will be depth to which your indenter is penetrating in the sample. So n plus hd, n minus hd, n times hd, and h minus nd. These are 4 options. So second one will be correct. Okay, so in case of Rockwell hardness number, your formula will be n minus hd, where n and h are the scale factors and small d will be depth of penetration in mm. So here the h value is 500 for scales B and C, and the n value is 130 and 100 for scales B and C respectively. Next question is, which materials are around 95% porous? Your options are aerogels, piezoelectric materials, amalgams, and Nitinol. So your correct answer will be aerogels. So as the name suggests, aerogels, so it will be consisting of porosity as high as 95%. Okay, so aerogels are 95% porous and are very light materials, and that's why these provide very highly thermal insulation as well. So they are used in making such as jackets and other applications for providing thermal insulation. And other is piezoelectric material. They convert mechanical stress into an electric signal and vice versa. And amalgams are mixtures of mercury and other metals which are used for dental fillings. Nitinol is an alloy of nickel and titanium. Now, which of the following is not a biomaterial? So biomaterial should be compatible with the human body, so they should not be toxic. So out of these, you can, by even looking at it, you can see that lead is toxic for humans. So this one won't be any biomaterial. Other options are PMMA, so polymethyl methacrylate, gold, lead, and calcium phosphate. So calcium phosphate is one of the ingredients used for making artificial bones as well. Gold is used in dental fillings, and PMMA is also used as biomaterial. So lead will be the correct answer. So lead is toxic to the human body, so it can't be used as biomaterial. While other materials, PMMA, gold, and calcium phosphate are used for various purposes as biomaterials. Next question is, the hardness of a material is the resistance of a material against. Your options are oxidation, indentation, twinning, and fatigue. So hardness is measured with the help of indentation type of machines. So it can be indentation based as well, scratch based as well, or rebound based as well. But other options are not given, only indentation is given. So indentation will be the easily correct answer. Okay, and here hardness is defined as the resistance of the surface of material against plastic deformation through indentation or scratch. And oxidation resistance is a chemical property, and fatigue resistance is also different from hardness. Next question is, ratio of elastic modulus and shear modulus is 3. Then what is the Poisson's ratio? So as we saw earlier, the relation between E and G, it was E equals to 2 times G and 1 minus mu. Okay, it was 1 plus mu. So you are given value of E upon G, so you have to find out value of mu. Okay, so you can easily calculate this. So you keep mu at one side, and then E upon G value is given 3. So 3 by 2 minus 1, the correct answer will be 0.5. What is the main advantage of using honeycomb type of structures in engineering applications? Now your options are high strain to weight ratio, low cost of production, easy manufacturability, or good electrical conductivity. So in case of honeycomb type of structures, I think you have seen honeycomb as well. So those are very light structures filled with a lot of hollow parts. So these also provide very good structural stability as well, along with the very light weight. So correct answer here will be high strain to weight ratio. Okay, so other advantages for honeycomb structure are given here. So some of the advantages are lightweight yet strong, and they have high compressive strength as well, efficient material usage because very less material will be used and a lot of hollow part will be there, and good thermal insulation will be there. They are resistant to corrosion, and some of the disadvantages will be they are difficult to manufacture, and they have less damage resistant, and they can be expensive and not suitable for heavy loads, and they are limited for material choices. Now some of the other questions from the lecture slides are, first question is, which is not an age from the archaeological sequence known as the 3-age system. So as you have gone through lecture slides or lecture videos, then I think you should know the correct answer. Three archaeological sequence are Bronze Age, Iron Age. Firstly, there will be Stone Age, then Bronze Age, then we have Iron Age. So depending on the these three, so Carbon Age won't be a part of this. Currently the age is called Carbon Age because or semiconductors that we use, so Silicon Age or Carbon Age. So here but this three archaeological sequence, in that we don't count this Carbon Age. Which materials form oxides which are basic? So you have various types of materials such as metals, non-metals, and ceramics, polymers. So out of these, which one forms oxides which are basic? So for example, you can think in the way, for example, aluminum, or rather than aluminum, you can think such as metals, iron or other metals which form oxide. So ferric oxide, what type of acid, whether it's acidic or basic. So depending on that, we can decide that metal oxides will be acting as basic, and your non-metal oxides such as phosphorus oxide or sulfur oxide, these act as acidic in nature. So with addition in H2O, they will form acids. So if you combine H2O and SO2, then it will be forming sulfuric acid. Lecture slides are visible. I'm expecting that lecture slides are moving and visible. If they are not, let me know. So we are going through some sample assignment questions. So third question is, which property is characteristic of ceramics? Your options are high electrical conductivity, good ductility, high compressive strength, or metallic luster. So in case of ceramics, they are oxides of metals. So these oxides or borides or nitrides, so these are in oxidation state already. So they are very poor conductors of electricity, most of them, and they have they are brittle as well. Okay, so they don't have good ductility as well, and they don't have metallic luster because they are ceramics oxides. Okay, so the correct answer will be high compressive strength, because in case of tensile loading they show poor strength, but in case of compressive strength they show good strength. Fourth question is, which material is 100 times stronger than steel and 6 times lighter? So your options are nitinol, amalgam, alumina and CNTs. So as you must have studied from the lecture slides or lecture videos as well. So carbon nanotubes are the materials which are very stronger as well as very light compared to steel. So they are around 100 times stronger and 6 times lighter from the steel. And then next question is, calculate engineering stress for a force of 2 kilonewton acting on a 3 centimeter diameter cylindrical rod. So in case of stress, the formula is simple. So S is equals to force upon area. So you are given force, you have to divide the area, the cross section area. Okay, so cross section area for 3 centimeter diameter. So you are given diameter, you can convert it into radius and then pi r square. Using that you can find out what will be the area, cross section area. Then you have to divide that with the 2 kilonewton and you will be getting the amount of engineering stress that will be acting. Okay, so the correct answer for this will be 2.8 megapascal. Okay, you have to take care of the units as well, because the diameter is given in centimeter and this one is given in kilonewton. So you have to take care of the units as well for getting, and then you will be getting it in megapascal. So mega is 10 to the power minus 10 to the power 6 times the pascal. Now we'll be going through some lecture notes. If you have any query from previous questions, then let me know. Otherwise, we'll go through lecture slides now. Okay, so firstly, history and evolution of materials. If you have any questions, you can ask. Okay, so we'll go through lecture notes. So firstly, history and evolution of materials. So materials are rooted in our culture and they have influence over virtually every segment of our daily lives. Okay, so for example, in transportation, housing, in for example in transportation, so we are using trains, cars and bikes. All these require, for the making of these you require some materials. For example, you require steels, aluminum and some composites. All those are required. In case of housing, in case of clothing, fabrics as well, they require either polymer or some cotton and other polymers which are natural. Communication, so for communication, for example your mobile phone as well, it requires a lot of materials. Recreational activities, those also require materials. Every civilizations have been designated by material development. For example, very previous times is given the title of Stone Age. So at that particular time, for making weapons as well, stone was used. And then it moved to Bronze Age, uh, which is alloy of copper and tin. Then we moved to Iron Age. After that, after which time we were able to form steel. Okay, so firstly we have Stone Age. So the term Stone Age was coined in the late 19th century by the Danish scholar Christian J. Thomson. It is roughly extended between 15,000 to 2000 before Christ. Now, it is characterized by the creation of use of stone tools, and also wood, bones and other materials were also used as tools but have had the shorter life. Okay, so these weapons you can see, weapons and tools which were made basically from stones. Then we had Bronze Age. It roughly extends between 3500 to 500 before Christ, and it is the beginning of metal working. So in this case, copper was mixed with tin to create new alloy, which was bronze, and it was stronger than other two metals individually. And because of the solid solution type of strengthening or the formation of intermetallics, these give the strength, these increased strength of pure copper and pure tin, both individually. Then these were used for tools, weapons, armor, decoration, etc. Now here you can see weapons made of bronze. Okay, daggers, kind of knives and swords. Then Iron Age. So it is the last stage of archaeological sequence known as the 3H system: Stone Age, Bronze Age and Iron Age. The Iron Age began with about 3000 years ago and it continues today. The use of iron and steel has changed drastically human development. It witnessed the Industrial Revolution, improved modes of transportation, automobiles, railways and aeroplanes. All these almost use steel and iron in some way or another. Then iron pillar. So it is a solid shaft of wrought iron which has high phosphorus content, about 7 meter tall, 0.4 meter diameter, weighing over 6000 kg. And it has high resistance to corrosion, which results from an even layer of the crystalline iron hydrogen phosphate hydrate, which serves to protect it from the effects of the local Delhi climate. Okay, so this hasn't rusted yet after so many years of its manufacturing. Then modern era of the steel making. So there are various years throughout which the steel making has changed. So firstly it was Bessemer process, so which was given by Henry Bessemer. So in this case steel mass production began with Bessemer converter. In this case air blast was injected into molten pig iron meaning which consisted a lot of carbon, from 3.5 to 4.5%. So for making steel, steel consists carbon percent below 2.1%. Okay, so and to reduce its carbon content, this air was blasted and it had some suitable for phosphorus free ores. So if it had very high amount of phosphorus in the ore, then this phosphorus will be remaining in the steel as well. Then in 1860 we had Gilchrist-Thomas process which showed improvement to the Bessemer process, and it used limestone to remove phosphorus. In 1865 Siemens-Martin or open hearth process was coined. So in this case it complemented the Bessemer process, melting iron bar or steel scrap with pig iron until carbon content was reduced by dilution and oxidation. So the steel scrap already had less carbon compared to the pig iron, so that's why this carbon got diluted. 1953 basic oxygen steel making. So in this case oxygen blast was used instead of air, and in latest electric arc furnace is used, which is highly efficient recycler of steel scrap. And then steel can be recycled endlessly with no detrimental effects on its properties. And all steel created as long ago as 150 years can be recycled and used in new products and applications. Next is material classification. So materials can be classified into 5 types. These are 5 large categories. Okay, so first is metals. So metals are on the left hand side of the your periodic table. On the right hand side you will be having non-metals, and in middle we have semi-metals as well, which are used as semiconductors such as silicon and others. So in case of metals we have ferrous and non-ferrous type of metals. In case of ferrous, iron and steel is there, and in case of non-ferrous we have copper, aluminum, titanium, gold, silver and tungsten. In case of non-metals, they can be existing in different type of physical states. So in case of gases we have hydrogen, helium, nitrogen, oxygen, chlorine, etc. And in case of liquid we have bromine. In case of solids we have carbon, phosphorus, sulfur, selenium, iodine, etc. In case of ceramics, these are the basically the materials which can withstand very high temperatures, and these are oxides, nitrides or borides, or even some elements as well. For example, diamond and graphite are elements, elemental form of carbon. Okay, so first we have alumina, silicon oxide, silicon carbide, and in case of polymers, these are the chains formed with the help of carbon and hydrogen, and their other elements can also be found such as fluorine, chlorine, bromine, etc. Now examples include wool, silk, which are natural polymers. Then we have artificial polymers such as polyethylene, PVC, nylon and bakelite. In case of composites, we have wood, concrete, fiberglass, CFRP, GFRP. CFRP is carbon fiber reinforced polymers, and GFRP is glass fiber reinforced polymers or plastics. Then we have category metals. So metals can be characterized by the following properties. If you have any query, you can ask, unmute yourself and ask. So in case of metals, we have their physical properties. So they are good electrical and heat conductors, and they are malleable, so they can be beaten into thin sheets. Ductile, so they can be stretched into thin wires. It's not moving. Okay, now metals are characterized by following properties. Okay. So they can be stretched into thin wires, and they possess metallic luster, and they are solid at room temperature except mercury. And the chemical properties include they usually have 1 to 3 electrons in their outer shell, and they can lose their valence electrons very easily, and they form oxides that are basic. So the oxides of these copper, zinc and tin, all these oxides will be acting as bases. and they are good reducing agents because they lose electrons easily, and they have lower electronegativity, so they have tendency to attract electrons. In case of non-metals, they are characterized by the following properties. So in case of physical properties, they are poor conductors of heat and electricity. And one second, the examples in case of metals, we have cast iron. So in this cast iron, iron is the base metal. So larger amount will be iron, and in case of wrought iron as well, iron, aluminum, steel, copper, zinc, brass, carbon steel, lead, tin, titanium, and alloy steel. Now steel, carbon steel, alloy steel, brass, wrought iron, and cast iron, these are alloys. Next, in case of non-metals, we have poor conductors of heat and electricity because they don't have that many free electrons. Then we have brittle. So these are, in case of solid state, they are brittle and they are non-ductile and they do not possess metallic luster and they are transparent as a thin sheet. Then solids, liquid, or gases at room temperature. So as I told earlier, and for different non-metals, they can be in different physical states. In case of chemical properties, they usually have 4 to 8 electrons in their outer shell, and they gain or share valence electrons easily, and they form oxides that are acidic, and they are good oxidizing agents, and they have very higher electronegativity. So diamond and coal are the examples of non-metals. Then ceramics. So ceramic materials are inorganic materials made from compounds of metal and non-metal, and they are formed by the action of heat and subsequent cooling, and they are brittle in nature and a good insulator of heat and electricity, and they have excellent compressive strength. So here we can see the roof tiles, these are made with the ceramics, and the bearings which use this these can use silicon nitride or silicon boride. These types of ceramics are also used in making ceramic bowls. Then for making potteries and for making ceramic coated turbine blades, these are some of the applications for ceramics. Next we have polymers. So a polymer is a large molecule composed of many repeated subunits, and first is natural polymers. So here shellac, which is a bioadhesive as well, amber, wool, silk, and natural rubber, these are some of the natural polymers. Then we have synthetic polymers. In this case, synthetic rubbers, bakelite, neoprene, nylon, polystyrene, polyethylene, and polyvinyl chloride, PVC, these all are some synthetic polymers, and these are some of the applications in making bottles, tires, and these snooker balls, helmets, spoons, these all are some of the applications of polymers. Next we have composites. So composites are will be having two or more constituent materials with significantly different properties, which are combination which after combination produces a material with characteristics different from the individual components. The individual components remain separate and distinct within the finished structure. So here fiber and matrix, these combined will give us composite. So instead of this fiber, they can be particle type of or viscous type of reinforcement as well, or some rods can be also there which can be inserted in matrix. Next is advanced and exotic materials, or also known as smart materials. So these can change their physical properties in a specific manner in response to specific stimulus input. And commonly used smart materials are piezoelectric. So these generate an electric charge in response to applied mechanical stress and vice versa. Next is magnetostrictive. So these change in the dimension of ferromagnetic material in a magnetic field and vice versa. And next is phase transition dependent. So these, remember, also known as these remembers its original shape and after being deformed returns to its original shape when heated. So these are also known as shape memory alloys. Next is electro or magnetorheological materials. So rheology is related to viscosity. So as you keep changing electric field or magnetic field, the viscosity of material will change. So change in viscosity in response to electric or magnetic field. Okay, so here we can see at a particular temperature lesser than this martensite finish temperature, below that if you deform your material martensite, deforming the martensite, then we increase the temperature, then this material will regain its original shape. So deformed martensite will, when it will go to austenitic phase and again go to martensitic shape, then it will regain its original shape. Next is biomaterials. So these are the substances excluding food and drug which are introduced into a living body with the aim of improving or replacing a diseased, damaged or lost tissue or a whole organ. Examples include biomedical applications, so joint replacement, bone plates, bone cement, artificial ligaments and tendons, dental implants, blood vessel and heart valves, skin repair devices, contact lenses. These all are some of the applications of biomaterials. Now, types of biomaterials. So they can be metals, polymers and ceramics. In case of metals, you have cobalt chromium alloys and stainless steel, gold, titanium alloys, Vitalium, which is cobalt, chromium and molybdenum alloy, and amalgams, which are alloys of mercury, Ag and tin. Shape memory alloys on nitinol, which is nickel titanium alloy, and copper, zinc and aluminum alloy. Usages can be in orthopedics, dentistry, etc. In case of polymers, we have silicons, polyethylene, which is ultra high molecular weight polyethylene. Okay, in polyurethanes, polymethyl methacrylate, PMMA, or bone cement, which is used for filling space between bone and implant. And in case of polymers, the usages in case of orthopedics, artificial tendons, vascular grafts, facial and soft tissue reconstruction, etc. In case of ceramics, alumina, calcium phosphate, which is used for bone grafting, synthetic hydroxyapatite, which is used for promoting bone ingrowth, pyrolytic carbon, which is lining on blood contacting processes, and here self-expanding nitinol stent is also shown. So its design is given in such a way that it self-expands according to the requirement. Then in case of aerogels, these are the materials which have around 90 to 98% porosity, and they are produced by extracting the liquid component of a gel through supercritical drying. The air molecules which are trapped inside the gel would act as insulators and its heat conductivity is close to 0. The applications include capturing space dust from comets, which was used in NASA Stardust mission in 19 199, and insulating material in space suits of NASA astronauts since the 1960s. Then we have potential applications, which are thermal barrier, which is extreme cold region clothes, such as for Siachen, which requires around 500 grams of gel to coat a jacket. Then we have thermal insulators for a cryogenic fuel tank of rockets. Then we have acoustic insulators, building and pipeline insulation. Next are superconductors. So this is in case it can be in form of an element, intermetallic alloy or compound which will conduct electricity without resistance below a characteristic critical temperature known as Tc. So these are very costly due to requirement of cryogenic temperatures, and some of the examples include mercury, lanthanum, barium, copper oxide, niobium, tin, yttrium, barium, copper oxide, etc. Next material is CNT, carbon nanotube. It was discovered in 1991 and it is composed of carbon atoms linked in hexagonal shapes. So here as it is seen. So in case of graphite, when you see, so one of the layers, if it is folded on its own, then it will form this carbon nanotube type of structure. So with each carbon atom, it is covalently bonded to 3 other carbon atoms, and carbon nanotubes have diameters as small as 1 nanometer and lengths up to several centimeters. The carbon nanotubes are the strongest and stiffest material yet discovered in terms of tensile strength and elastic modulus respectively. And these CNTs are at least 100 times stronger than steel but only 1/6 as heavy. And they are extremely high thermal conductivity, such as 10 times of the copper, and electrical conductivity 100 times the of copper. Now combining carbon nanotubes with other materials into composites can be used to reinforce and build lightweight structures. Okay, so these are used in reinforcing other materials as well. So in case of metals also you can reinforce CNTs. Next, classes of property which affects the product designs. So these are the classes. So first is economic and environmental class of properties, which include price and availability, recyclability, sustainability, and carbon emission. Next we have mechanical properties, which include modulus, yield and tensile strength, hardness, fracture toughness, fatigue strength, creep strength, and damping. Next is thermal. So in this case we have thermal conductivity, specific heat, thermal expansion coefficient. In case of general physical property we have density. In electrical and magnetic properties we have resistivity, dielectric constant, and magnetic permeability. Next, in environmental interaction we have oxidation, corrosion, and wear. In case of production based class we have ease of manufacturing, joining, and finishing. So how easily a material can be joined with the help of welding or other processes, or how easily it can be surface finished. Aesthetic, so for its color, how its texture can be changed. These will be in case of aesthetic class. Next we have mechanical properties. So these are some of the examples of mechanical properties, such as tensile strength, ductility, brittleness, resilience, toughness, and impact strength. So for selecting a material for a particular application, if you want to build a window with the help of some material, then you'll be considering these mechanical properties so that it can sustain that much strength, that much load, and other. It can be built in thin form, a plate type of form. So for that you require it to have malleability, and you don't require it to be brittle. If it's brittle, then it might fracture without giving any prior alarm. Okay, so in case of resilience, these properties will talk later based on this particular stress strain curve. So in case of stress strain curve, with this can be divided into three categories. So firstly, you have elastic deformation, in which you have a stress strain are linearly proportional. Okay, so this is Hooke's law. So your stress is proportional to strain, and the proportional constant will be Young's modulus, okay, which is slope of this curve. Then you have uniform plastic deformation after yield point. Okay, so yield strength will be the stress corresponding to this yield point, and after that you have this uniform plastic deformation, and this will reach here at this point UTS, ultimate tensile strength, maximum strength, which after that necking will start. So your cross section will start to get very low at this point. Okay, so at a particular point necking will start, then non-uniform plastic deformation will start, and then finally fracture will take place. Now next, need to determine mechanical properties. So how to determine mechanical properties? So firstly you will be performing a test such as tensile testing, then you will be capturing data which will be in terms of load and displacement. Okay, now this data is converted with the help of sample parameters. So you will be dividing your load with your cross sectional area and finding out the stress, and you will be dividing the displacement with the initial gauge length. So you will be getting strain. Okay, so stress strain curve, with the help of that you can find out fracture strength, UTS, yield point, the elastic modulus, and other properties. So after statistical analysis you can get various mechanical properties, and based on that you can design your material, and you can find out how much material you require, so that you don't use extra material and you can make it cost effective. Okay, so your product will be profitable. Next we have stress and strain. So stress can be of two types. It can be engineering strain, and then it can be true stress. Okay, so in case of engineering strain, here the internal resistance force per unit area which is acting on a material. So it uses the original cross section area of the specimen and is also known as engineering stress or conventional stress. Okay, so sigma is equals to F upon A naught, cross sectional area, which is original area. If it is instantaneous area, then it will be true stress. The unit of stress will be Pascal or Newton per meter square. Okay, so here in this rod as well we can see cylindrical rod we have. So its initial area was A naught, then it changed, final area changed to, it became lesser than A naught. Okay, so length changed, length increased to L. Initially it was L naught. So using these factors you can calculate stress. And here you are applying tensile type of loading. Here you are compressive type of loading. So in case of compressive, your area will increase and the length will decrease. Now in case of strain, it is defined as the change in length per original length. So you have to divide your change in length, delta L, displacement, divided by original length, and it is unitless and also known as engineering strain or conventional strain or normal strain. Okay, so E can be given as delta L upon L naught. Sometimes strain is expressed in microstrain. So 1 microstrain will be equals to 10 to the power minus 6. Now in case of Hooke's law, this is the proportional region where the elastic limit is followed. So within the elastic limit, for the low strain values, the stress is directly proportional to strain, and the behavior of the solid is linear elastic. The constant of proportion is called the elastic modulus, and the sigma is equals to capital E times epsilon. So epsilon is your strain, capital E is your elastic modulus, sigma is stress. So it also holds good for stresses and strain in simple compression. So in the same way, shear stress tau is proportional to shear strain gamma. So tau equal to capital G times gamma, where G is the shear modulus. In case of the pressure, pressure is proportional to the negative of the dilation, which is volumetric strain. And because positive pressure causes a shrinkage of volume, hence capital P is equals to minus K times delta V upon V. Here K is the bulk modulus, and all these three modulus, this K, G and capital E, these all have the same dimension as that of stress, which is Pascal. Okay, so from this stress strain graph also you can see the slope of this part, linear part, will be Young's modulus, and after this yield strength you will be getting strain hardening part. So here dislocation will start to multiply and will start making your material harder compared to initial, and after this necking will start and then fracture. Elastic limit, it is the greatest stress that material can withstand without any measurable permanent strain after unloading. And the yield strength, so here stress at which a material begins to deform plastically. So before this your material will deform elastically. So as soon as you remove the load that is acting on the material will regain its original shape, original size and shape, while if it crosses the elastic limit, then it will deform permanently. Next is yield strength. So stress at which a material begins to deform plastically, and it is determined by the stress corresponding to the intersection of a stress strain curve and a line parallel to the elastic line offset by a strain of 0.2%. So strain will be 0.002. So for example, in this material it's easy to decide where the yielding is beginning, but in some other cases your graph may look like this one where the yield point is not visible. So here what you do, you find out, you take a offset of 0.002, then parallel to this line you draw a line, so where this will cut this graph, then corresponding to that on y-axis you will be getting that stress value as the offset yield stress. Okay, so next is tensile strength or ultimate tensile strength. It is the maximum load P max divided by the original cross sectional area A naught of the specimen, and then we have elongation, which is final length minus initial length divided by initial length times 100. So it will be in percentage. Next we have reduction in area. So this is also measured in some samples. So this will be final area minus initial area divided by initial area times 100. Now in case of true stress and true strain, so in case of true stress true strain curve, it gives a true indication of deformation characteristics because it is based on the instantaneous dimension of the specimen. In engineering stress strain curve, stress drops down after necking since it is based on the original area. In true stress strain curve, the stress however increases after necking since the cross-sectional area of the specimen decreases rapidly after necking. So in this area, this is the flow curve known as flow curve before m dot. Okay. So in this area, this equation is followed. The flow curve of many metals is the region of uniform plastic deformation, which can be expressed by a simple power law. So here sigma t is equals to k times epsilon t times n. So n will be strain hardening exponent, k is strength coefficient. So n can be 0 for perfectly plastic solids and n can be 1 for elastic solids. And for most metals, it's seen that n is between 0.1 to 0.5. Now, other property of material is ductility and brittleness. These are opposite properties. So, if a material is ductile, then it won't be brittle. If it's brittle, then it won't be ductile. So, ductility, it measures the degree of plastic deformation that has been sustained at fracture. So, if strain at fracture is greater than 0.05 or 5%, percent elongation is greater than 5%, then it is a ductile material. So it has well defined yield point. And if a material is brittle, then a material which experiences very little or no plastic deformation upon fracture. So strain at failure is less than 0.05 or percent elongation is less than 5%, and it does not exhibit an identifiable yield point. Okay, so here you can see these are two stress strain curves, which is one corresponds to brittle material, other corresponds to ductile material. So in case of ductile material, we will be having a lot of area under the curve compared to brittle material. So brittle material won't go into permanent deformation part as well. So for material, this is what brittle. Here this is the process of ductile failure. So firstly there will be necking formation. So cross section area has decreased a lot compared to original area. So here void will nucleate and these voids will collapse, and then at a particular angle to the application of stress, this material will show failure. So crack initiation and crack propagation will occur at a particular direction. Then we have resilience. So resilience is the capacity of a material to absorb energy when it is deformed elastically, and then it recovers same upon unloading. Okay, so here we can see up to yield point, the area under the curve will be resilience. Okay, so this is the capacity of material to absorb energy when it is deformed elastically, and then it also recovers upon unloading, because up to elastic limit, if you remove the load, then it will regain its original shape and size. So then we have modulus of resilience, which is the strain energy per unit volume required to stress a material from an unloaded state up to a point of yielding. So SI unit for this will be joule per meter cube. Okay, so this will be this is denoted with the help of capital U. R equals to half times sigma and strain, yield stress times yield strain. So here, as it is forming a good triangle, so here we are just multiplying this elastic strain to the elastic stress times half, because it is forming a triangle compared to this. Okay, so this, with the help of Hooke's law, this epsilon y can also be written as sigma y upon capital E, which is elastic modulus. So in terms of elastic modulus also, this can be written as sigma y squared divided by 2e. Okay, so for resilient materials, they have high yield strength and low modulus of elasticity. For example, in case of beryllium copper, which is used for spring applications, because in case of spring, as soon as you release the load, it should come to its original shape. Spring, it should not lose its original shape. Okay, so for in case of spring materials, the resilience is very important property. Next we have toughness. So toughness is the measure of the ability of material to absorb energy up to the fracture. So previously we only counted area under the curve up to yield point, but here up to fracture point will be counting the area. Okay, so it is measure of ability of material to absorb energy up to fracture. So a material which will be having higher ductility as well as combination of ductility and combination of UTS, high strength, then your material will have high toughness. If it has lower ductility and high strength, then again it will have lower toughness. Okay, and it is represented by the total area under the stress strain curve up to the fracture point. The brittle material, they have comparatively high yield and tensile strength, but they have low toughness due to lack of ductility, and the ductile materials are tougher compared to brittle ones. Okay, so as we know, ductility will be counting to the x-axis, while high UTS will be counting to the higher position in the y-axis. So that's why it's written that ductile materials are tougher compared to brittle ones, because it has higher area under the curve. Next we have impact testing. So in this case, load will be swinging from a given height to strike the specimen, and the energy is dissipated in the fracture which is measured. Okay, so metallic samples tend to be square in cross section, while polymeric test specimens are often rectangular. So the factors which affect impact energy. So for a given material, the impact energy will be seen so we are going to do you have any query? You can ask if you have any query, otherwise you can mute yourself. So we are going through lecture notes. So in case of impact testing, in these tests, load swings from a given height to strike the specimen, and the energy that is dissipated in the fracture is measured. So in this case, compared to the toughness, static toughness, we count the area under the curve, but in this case the area under the curve will be very less, because you're applying you're swinging the load at very higher rate. In this case, we change the strain rate at very slow rate. Here the strain rate is very high. So the metallic samples, they tend to be square in cross section, while the polymeric test specimens, they are often rectangular. The factors which can affect impact energy, first is, for a given material, the impact energy will be seen to decrease if the yield strength is increased. So if we are able to increase yield strength of material by some method, such as if we are using quenching of material to increase the yield strength, then it will be showing less impact energy. Okay, and next is the notch serves as the stress concentration zone. So if your material has some notch or pre-existing cracks, then it will be showing less impact energy, and some materials are more sensitive towards notches compared to others. So most of the impact energy is absorbed by means of plastic deformation during the yielding, and therefore factors which affect the yield behavior and hence ductility of the material such as temperature and strain rate will affect the impact energy. So for various materials we can see ceramics have very low impact energy because they are very sensitive to pre-existing cracks, and they don't have as much ductility as seen in metals and polymers. And metals have very high impact strength compared to ceramics. Then polymers and composites, they have some optimum impact strength. Next we have hardness. It is a measure of a material's resistance to localized plastic deformation, and this plastic deformation can be in form of indentation or scratch or rebound as well. So advantages of hardness testing. So this is a simple and inexpensive technique, and it requires no special specimen preparation which is needed in case of other techniques such as tensile testing or fatigue testing, and the apparatus that used is also relatively cheaper compared to other testing machines, and it is also non-destructive method. So there will be only formation of a small indentation in case of hardness. So other mechanical properties like tensile strength and fatigue strength, they can be obtained from the hardness data. So there are some empirical relationships between hardness and fatigue strength and this tensile strength, ultimate tensile strength. So by using those for particular material, for example brass and steel, these empirical relationships exist. So we can tell what will be the range of the tensile strength if we just measure the hardness of the material. Now hardness test, firstly we have Mohs scale. So in this case it is based on the ability of one material to scratch another. So these are minerals such as talc, diamond, corundum and others. So in this case hardness is measured on a scale from 1 to 10, 1 being the softest, 10 being the hardest. In case of macro hardness test, we have other tests such as Rockwell, Brinell and Vickers hardness. In case of micro hardness test, we have Knoop and Vickers micro hardness test. So for these materials you can be asked in questions as well, so you should remember some of these Mohs hardness for these minerals. For diamond being 10, talc being 1, then you have gypsum, calcite, fluorite, apatite and feldspar, quartz, topaz and corundum. Now these are other tests such as Brinell, Vickers, Knoop, Rockwell and the indenters that are used, and what are the hardness number, what are the formula that are used. So in case of Brinell hardness test, the indenter that's used is 10 mm steel ball or tungsten carbide ball. So the side view and top view is similar because it's a ball, so it will be circular cross section. Okay, so indentation and indenter diameter are given. So indenter diameter is capital D, small d is the diameter of indentation. Okay, so and loads can be varied between 500 to 3000 kilograms. Okay, and the formula will be 2 times load divided by pi d and brackets d minus under root t square minus small d square. In case of Vickers, you have diamond pyramid of the indenter. So it is made of diamond and the angle between these axes will be 136, and this is what your indentation looks like. So you measure the diagonals of this, and these diagonals are referred as capital L, and you put this in this formula and the load is varied between 1 to 120 kilograms. This can be in grams as well. In case of micro hardness testing for pickers, this load can be in grams as well. And the formula used is 1.854 times load divided by diagonal square. In case of NPTEL, your diamond pyramid is used and the L upon B is 7.11, B upon T equal to 4. So here T is the depth of penetration. Okay, so here you will be measuring the longer diagonal only, and this capital L is used in this formula, and the load that's used between 25 gram to 5 kg. In case of Rockwell, you can use different type of indenter. It can be either diamond cone or it can be steel ball of different diameters as well, 1 upon 16 inch to 1 upon 8 inch. Okay, so depending on various scales, so for soft materials you use steel ball, and for hard materials such as martensitic steel and other steels you use diamond cone. Okay, so this is what diamond cone looks like, and this is what steel ball will look like, and these are the impressions left on the material. So the loads that are used for various ACD scale will be 60, 150 and 100 kg. And for BFG scales, the loads used are 100, 60 and 150 kg. In case of E scale, the load used is 100 kg. And these are the formulas that are used. So as I told earlier as well in one of the questions, N minus HD. So H will be your N and H are the scale factors. So it is used in ACD scale, it is used 100 and 500, and in case of BFGE, these scales, it is used 130. T is your depth of penetration. Next is Rockwell hardness test. So how this test looks like? So firstly, there is minor load is first applied for a good contact between indenter and the sample surface. So this is applied. So if your surface finish is not very good, in that case also this removes that type of effect to be considered into your measured hardness. So between the indenter and the sample surface followed by a major load, and the depth of indentation is recorded on a dial gauge after removing major load. Okay, so firstly you are applying minor load, then major load is applied, and then on removing of this major load, this penetration of depth is measured, and based on that your hardness will be measured. So in this case, a cone shaped indenter for harder materials or a small diameter steel ball is pressed into a specimen. Okay, this is what your instrument will look like. Here various terminologies are given. So small e is the permanent increase in depth of penetration due to major load. Capital E is a constant depending on form of the indenter, which is 100 units for diamond indenter, 130 units for steel ball indenter. HR is Rockwell hardness number, E minus small e. Okay, so these are various scales that are used, and these are the corresponding indenters, okay, and corresponding loads. And so typical material that are tested for A type of scale are carbides and ceramics. In case of B scale, you use non-ferrous metals which are softer, and in case of C scale, you use ferrous metals and tool steels which are harder compared to your steel balls, so you use diamond indenter. Next is Brinell hardness test. It is used for testing metals and non-metals of low to medium hardness. So in this case, the hardened steel or cemented carbide ball is used of 10 mm diameter. It is pressed into the surface of a specimen using load of 500, 1500 and 3000 kilogram force for a specified time between 10 to 30 seconds. Okay, so the formula that I already told, this is used, and the hardness is unit is shown with the HB, meaning Brinell hardness number, and its unit is kgf per mm square, and P is the applied load in kilogram force, and where mean indentation diameter is measured. So two diameters you measure on your sample and then you get a average diameter. So thumb rule for the steel alloys is that tensile strength is 3.45 times the Brinell hardness. Next we have Vickers hardness test. So in this case, Vickers test uses a square base diamond pyramid indenter using an angle of 136 degree between the opposite faces, and the hardness is obtained by dividing the load 1 to 120 kilogram force with the surface area of the indentation. The surface area is calculated from the diagonals length of the impression. Okay, and here after measuring the diagonals, this is capital L and F is force that is applied load in kgf, and L is diagonal length of the impression in mm. Next property is creep. So it is the permanent deformation under constant load over a period of time, and it is dependent on temperature. So as you keep on increasing temperature for a particular material, your creep will keep on increasing because of the easier diffusion of in material. A creep test involves a tensile specimen under a constant load maintained at a constant temperature. At relatively high temperatures, creep appears to occur at all stress levels, but the creep rate increases with increasing stress at a given temperature. Application: it's for studying material behavior at elevated temperatures such as turbine blades, nuclear reactor components, jet engines, heat exchangers, etc. And creep occurs in three stages. Primary stages, it occurs at the beginning of the test, and creep is mostly transient. Secondary stage, in this case creep rate is roughly steady, and in tertiary stage creep rate begins to accelerate as the cross-sectional area decreases due to necking and followed by failure. So this is your creep testing. Here specimen is given here. So it is a dog bone shaped type of specimen. Here you are measuring extension, which is measured over gauge length, and the constant force is applied and particular temperature is maintained. Okay, so as I told earlier, it occurs in three stages, and then at temperature lesser than 0.4 times the melting temperature and after the initial deformation, the strain is virtually independent of time, and with either increase in stress or temperature, the creep strain increases and the rupture life reduces. Okay, so mnemonic 95 has been certified by the European Union as a standard creep reference material, and these mnemonics are nickel based, high temperature, low creep super alloys which contain more than 50% nickel and 20% chromium with additives such as titanium and aluminum. And these are what creep curves looks like. So with time your strain will change and stress is maintained at a constant. Okay, so in case of primary stage, there is firstly instantaneous deformation, then there is increase in strain, then there is steady state or secondary stage, then there is tertiary, after that rupture will occur. Okay, so with increasing temperature and increasing stress, how these curves will change. So rupture will occur faster and this strain will happen faster in case of increased temperature and increased stress. Now other property is damping property. So it is a method, it is used in case of, for example, if you are using for lathe machine, we use beds for this made of cast iron. So because cast iron show good damping property, so that's why they are used. So for understanding which material to use, you need to understand what is damping. So firstly, to reduce the vibrations, the methods for reduction are, first you can increase the damping capacity or you can increase the stiffness. And damping here refers to the dissipation of energy from a vibrating system. And the damping force magnitude is generally smaller than elastic and inertia forces. And even if the damping force is smaller, it is important for controlling vibration, particularly near resonance. And the advantages of this is the shock absorption will occur, fatigue failure will be prevented, and noise reduction will occur. So for using these damping materials, these three advantages can be seen. So lecture slides are up to here. So now we'll go through the questions once again. Okay, so initially we talked about the sample assignment questions, so we'll go through them again. So first question, in a standard tensile test near elastic limit zone, then you have to fill in the blank. First question is, tensile stress increases in linear proportion to the stress, or tensile stress increases at a faster rate, tensile stress decreases at a faster rate, or none of the mentioned. So the correct answer will be tensile stress decreases at a faster rate. So for answering these type of question, you should remember stress strain curve in your you should remember this stress strain curve for particular materials. So initially your stress and strain will increase. Stress will increase with stress proportionally up to yield point. After that, you have to decide your stress will reduce. It decreases at a faster rate. So during tensile testing, if the material is stressed beyond elastic limit, the tensile strain increases faster as compared to stress. Second question is, what do the two subscripts of stress tensors represent? So your options are directions of the stress and strain, or directions of strain and normal to the surface on which they are acting, direction of stress and normal to the surface on which they are acting, or direction of stress and the flow direction. So as we know, stress tensor will only represent stress, so the strain including answers will be incorrect. So out of these two, one of them will be correct. So in case of stress tensor, the other subscript always represents normal to the surface on which they are acting. So third one will be the correct answer. In this specimen also, you can see with the if it's acting in direction 3 and acting on surface 3, then it is 3 3, and 3 1, here it is acting on surface 1 and in direction 3. Okay, so using this particular image, you can remember what will be the two subscripts. Next question is, which statement is correct? Your options are, necking starts at a yield point, yield point phenomena are seen in aluminum, or endurance limit can be determined by tensile testing, or yield strength is structure sensitive property. So as we know, necking starts at ultimate tensile strength point, and UTS point and yield point phenomena is seen in materials which have interstitial atoms to it, while in pure aluminum it won't be showing yield point phenomena. Endurance limit can be determined by using fatigue test, not tensile testing. So initial three statements are incorrect. Yield strength is structure sensitive property, which is a correct statement. Okay. So yield strength of material, it changes with microstructure. For example, annealed, normalized and hardened steel of the same composition will show different yield strengths. And necking starts at the UTS point, and the yield point phenomena are seen in alloys with small amounts of interstitial atoms such as mild steel. Next is endurance limit can be determined by fatigue testing, while tensile testing gives tensile properties such as E, S, E, yield strength, etc. So it can give elastic modulus, stress, strain and yield strength, etc. Next question is, what is the ratio of Young's modulus of elasticity to the modulus of rigidity in terms of Poisson's ratio, mu? So your options are 2 times 1 plus mu, 1 plus mu, 1 minus mu, or 2 times 1 minus mu. So the correct answer will be first one. So this particular relation you should remember. In lecture slides it is given, and there are various numericals asked based on this question as well. So it can be asked in exam as well. So you should remember this particular relation. So your elastic modulus is equals to 2 times shear modulus times 1 plus Poisson's ratio. Okay, so E upon G is the ratio. It is equals to 2 times 1 plus mu. So E will be elastic modulus, G will be shear modulus. Now what is the formula for Rockwell hardness? So your options are N plus HD, N minus HD, N times HD, or H minus ND. So correct answer here will be second one. Here N and H are the scale factors and D is the depth of penetration in mm. Okay. So in case of Rockwell hardness, number is given by N minus HD. So here H value is 500 for scales B and C, and the N value is 130 and 100 for scales B and C respectively. Now which materials are around 95% porous? Your options are aerogels, piezoelectric materials, amalgams, nitinol. So which one would be correct? So the correct answer will be aerogels. So aerogels are 95% porous and hence they are very light materials. And as the name suggests, aerogels, so there will be air gap between these gels. So it will be 95% air in the aerogels. So they are very light materials and they also have very good thermal insulation. Next is piezoelectric materials. So these are materials which convert mechanical stress into electric signal, or these can also convert voltage into mechanical strain. Amalgams are mixtures of mercury and other metals which are used as dental cylinders. Nitinol is the alloy of nickel and titanium. It is a smart one of the shape memory alloys. Which of the following is not a biomaterial? So your options are PMMA, gold, lead and calcium phosphate. So as I told earlier, biomaterials should not be toxic for body. So they should be, here correct answer will be lead, because lead is toxic for human body, so it can be used as biomaterial. Gold is used as dental implant. Calcium phosphate is also used as biomaterial, and PMMA is also used as biomaterial. Okay, so lead is toxic, so it can't be used as biomaterial, while other materials, polymethyl methacrylate, gold and calcium phosphate are used as biomaterials. Eighth question is, the hardness of material is resistance of a material against. So as I told earlier, it's deformation, resistance against plastic deformation, which can be in form of indentation or scratch. So here only option available is indentation. So indentation will be correct answer. Okay, so hardness is defined as the resistance of surface of material against plastic deformation through indentation or scratch. Next is oxidation resistance is a chemical property, and fatigue resistance is also different from hardness. Next is ratio of elastic modulus and shear modulus is 3. Then what is the Poisson's ratio? So as I told earlier, this is the formula that you have to use. E upon G is given, and with the help of E upon G is 3. So 3 by 2 minus 1 would be the answer for Poisson's ratio. So it will be 0.5. Okay. So you have to just put the values of E upon G and you can find out Poisson's ratio. What is the main advantage of using honeycomb structure in engineering applications? So your options are high strain to weight ratio, low cost of production, easy manufacturability, good electrical conductivity. So your correct answer will be high strength to weight ratio. So other advantages of using honeycomb structure will be they have lightweight but they are strong, they have high compressive strength, efficient material usage and good thermal insulation. They are also resistant to corrosion, and disadvantages include difficult to manufacture, they are less damage resistant, they can be expensive, and they are not suitable for heavy loads, and they have limited material choices which can be converted into honeycomb structures. Now some other questions. So which is not an age from the archaeological sequence known as the 3-age system? So your options are Bronze Age, Iron Age, Stone Age and Carbon Age. So from lecture slides also you will read and you'll be knowing the answer that these 3 ages are the part of the archaeological sequence. Carbon Age not a part of this system. Next is which material forms oxides which are basic? So your options are metals, non-metals, ceramics and polymers. So iron, copper, the oxides related to these, also zinc oxide, all these oxides act as basic. So as you will be adding them into water, they will be forming bases. And for example NaOH, so if you add your sodium oxide in water, it will be forming base. So these will be acting as basic oxides. Which property is a characteristic of ceramics? So ceramics, they are insulators of thermal and electrical signals, and also they are very brittle, so they are not good they don't have any good ductility. They are also electrically insulating, so this option is also incorrect. And high compressive strength. So in case of ceramics, they have low strength in case of tensile type of loading, but in compressive loading they show high compressive strength. They also don't have any metallic luster. Metallic luster is only seen in case of metals. Next is which material is 100 times stronger than steel and 6 times lighter? And your options are nitinol, amalgam, alumina and carbon nanotubes. Okay, so correct answer will be CNTs. So CNTs, they have very high strength compared to all the materials that we have tested yet, and also it is very lighter compared to iron, this steel, because steel will be consisting of iron, which is heavy metal, compared to carbon, that is CNT is manufactured from. Calculate engineering stress for a force of 2 kilonewton acting on a 3 centimeter diameter cylindrical rod. So stress formula is uh, simply force divided by cross sectional area. So force is given 2 kilonewton. So 2000 divided by your area will be pi r square. Okay, so 3.14 times your, you have to convert your diameter into radius. So 3 by 2, 3 by 2, and then centimeter also need to be converted into meter. So after taking care of all these units, you will be getting your correct answer will be around 2.8 megapascal. History and evolution of materials. So I'll be going through lecture slides once more briefly. So materials, they are rooted in our culture and they have influence over virtually every segment of our lives, such as in transportation, housing, clothing, communication, recreation, etc. And the early civilization are designated even by material development, such as Stone Age, Bronze Age and Iron Age. So earlier, Stone Age, it was coined for late 19th century, in the late 19th century by Christian J. Thompson, and it roughly extended between 15,000 to 2000 before Christ, and it is characterized by creation and use of stone tools. Other materials were also used, but not to that extent, and their life was also shorter. Then there is Bronze Age. So it roughly extends between 3500 to 500 before Christ, and it is beginning of the metal working. So here copper is mixed with tin to create an alloy which was stronger compared to copper and tin individually. And the tools that were used, weapons, armors, decorations, they all were made using bronze. Then Iron Age, in this case steel is used, which is part of all transportation such as automobile, railways and aeroplanes. All these consisted of steels. Now iron pillar is so it is a solid shaft of wrought iron. So in this case a lot of phosphorus content is there, so there is a fused layer, crystalline layer of hydrogen phosphate hydrate, and it provides the protection against the corrosive environment of Delhi. Then these are the up to this era, how we transformed to this era for the steel making. So these were various practices that were used before. So Bessemer converter, and then the open hearth process, then basic oxygen steel making, electric arc furnace is currently used. So in this case, this is basically highly efficient for recycler of steel scrap. Then material classification. So engineering materials can be classified into 5 big classes. Metals, in which you'll be again having subcategories such as ferrous and non-ferrous. In case of ferrous, these will be iron based materials. So iron, steel and cast irons. In case of non-ferrous, we'll be having other metals other than iron. So copper, aluminum, titanium, gold, sodium, all these will be non-ferrous metals. Then in case of non-metals, you have 3 physical classes: gases, liquid, solids. So in case of gases, you have hydrogen, helium, nitrogen, chlorine, oxygen, etc. In case of liquid, only bromine is there. Then in case of solids, carbon, phosphorus, sulfur, selenium, iodine, etc. In case of ceramics, these are the basically a combination of metal and non-metal, and also in elemental form carbon as well is sometimes known as ceramics. So diamond and graphite are ceramics because they can sustain very high temperatures. So alumina, silica, silicon carbide, zirconium oxide, all these are ceramics. Polymers, so these are the hydrocarbon chains. So these can be synthetic or natural. Composites are the combination of different categories of materials. Then we went through metals. So in case of metals, they are categorized by physical properties. So they have good electrical and heat conductivity. They are malleable, can be beaten into thin sheets, and they can be stretched into thin wires as well. And they possess metallic luster. They are solid at room temperature except mercury, and they usually have 1 to 3 electrons in their outer shell, and they lose their valence electrons very easily. That's why they are very highly electrically conductive. They also form oxides, which are basic, and they are good reducing agents because they lose electrons, and they have lower electronegativity. So tendency to attract electrons is less in case of metals. These are the examples. In case of non-metals, they are poor conductor of heat and electricity, and they are brittle in case of solid state, and they are non-ductile. So brittle basically means non-ductile, and they do not possess metallic luster. They are transparent as thin sheets, and they are solid, liquid and gases at room temperature. And the chemical properties, they usually have 4 to 8 electrons in their outer shell, and they gain or share valence electrons very easily, and they form oxides that are acidic. They are also good oxidizing agents, and they have higher electronegativity. Ceramics are materials which are inorganic materials which are made of compounds of metal and non-metal, and they are formed by the action of heat and subsequent cooling, and they are brittle in nature, and they are good insulator of heat and electricity, and they possess very good compressive strength. Polymers are large molecule composed of many repeated subunits, so they can be natural or synthetic. Two or more constituent materials with significantly different properties, which after combination they produce a material which has characteristics different from the individual components, and the individual components remain separate and distinct within the finished structure. So they'll be having a physical boundary between these two structures. They won't be combining. Okay, so they will be having two parts, reinforcement and matrix. Okay, so reinforcement can be fiber, particles, whiskers, rods and other forms. Now next is smart materials. So these can change their physical properties in a specific manner in response to specific stimulus input. Commonly used smart materials are piezoelectric. So these generate electric charge in response to applied mechanical stress and vice versa. Then we have magnetostructive, which can change the dimension of ferromagnetic material in a magnetic field or vice versa. And in case of phase transition dependent, these remembers its original shape, and after being deformed, they return to its original shape when heated. Electro and magneto-rheological materials, they change in viscosity in response to electric and magnetic field. Next we have biomaterials. So these are substances excluding food and drugs which are introduced into living body with the aim of improving or replacing a diseased or damaged or lost tissue or a whole organ. These are the materials that are used as biomaterials. In case of metals, you have cobalt chromium alloys, stainless steel, gold, titanium alloys, metallurgium, amalgams, shape memory alloys, copper, zinc, aluminum, etc. In case of polymers, we have silicons, polyethylene, polyurethanes, polymethyl methacrylate, and in case of ceramics, you have alumina, calcium phosphate for bone grafting, synthetic hydroxyapatite to promoting bone ingrowth, and pyrolytic carbon, etc. Next category is aerogels. So aerogels are materials that has around 90 to 98% porosity, and they are produced by extracting the liquid component of a gel through supercritical drying. The air molecules that trapped inside the gel would act as insulators, and its heat conductivity is closer to zero. Their applications are in capturing space dust from comets and insulating materials in space suits of NASA astronauts since 1960s. Potential applications. So firstly, thermal barrier. So in extreme cold region, clothes such as for Siachen, and for thermal insulators for a cryogenic fuel tank of rockets, acoustic insulators, building and pipeline insulation. Next category is superconductors. So in this case, an element, intermetallic alloy or compound, which will conduct electricity without any resistance below a characteristic critical temperature Tc. And these are very costly due to cryogenic requirements. So some of the examples are mercury, lanthanum, barium, copper oxide, niobium, tin, yttrium, barium, copper oxide. Then we have carbon nanotubes. So these were discovered in 1991, and these were composed of carbon atoms linked in hexagonal shapes, with each carbon atom covalently bonded to 3 other carbon atoms. The carbon nanotubes have diameters as small as 1 nanometer and lengths up to several centimeters. Carbon nanotubes are the strongest and stiffest materials yet discovered in terms of tensile strength and elastic modulus respectively. CNTs are at least 100 times stronger than steel but only 1/6 as heavy. So they also have extremely high thermal conductivity, around 10 times of copper, and electrical conductivity around 100 times of copper. And these CNTs are also used as reinforcement in case of polymers and metals as well. Next is the classification of properties based on product design. So some of the classes are economic and environmental classes, which includes price and availability, recyclability, sustainability, carbon emission. Mechanical class consists of mechanical properties such as modulus, yield and tensile strength, hardness, fracture toughness, fatigue strength, creep strength, damping, etc. In case of thermal properties, thermal conductivity, specific heat, thermal expansion coefficient. In case of general physical, there is density, electrical and magnetic properties. We have resistivity, dielectric constant, magnetic permeability. In case of environmental interaction, we have wear, corrosion and oxidation. And in case of production, ease of manufacturing, how easily a material can be joined after breaking, and the surface finishing. And in case of aesthetic, we have color and texture. Now in case of mechanical properties, these are measured using this tensile test after getting stress strain curve. So using this you can find out tensile strength, ductility, brittleness, resilience, toughness, and impact strength is something that is measured separately, not using stress strain curve. So if you need to determine mechanical properties, you can perform tensile test, then capture data, then on analysis you can get various mechanical properties, and based on those properties you can design your material, and you can use your material efficiently, and you can get profit by using efficient amount of material. Then stress strain, so the internal resistance force per unit area which is acting on material, and it uses the original cross section area of the specimen, is also known as engineering stress or conventional stress. And if you use instantaneous area, then it will be true stress. In case of strain, you have defined as the change in length per unit original length. Okay, so it is unitless and also known as engineering strain or conventional strain or normal strain. So if you divide this by instantaneous length, then it will be true strain. Then we went through Hooke's law. So it is the linearity initially in elastic region. So as much as stress versus strain curve, so the slope will be Young's modulus. Okay, so this type of this proportion region, it will be also in case of simple compression. So in the same way, shear stress tau is proportional to shear strain. So tau will be equals to G times gamma. And in case of pressure as well, pressure will be equals to minus K times delta V upon V. So here K is the bulk modulus. Then elastic limit. So it is the greatest stress that material can withstand without any measurable permanent strain after unloading. And yield strength is stress at which a material begins to deform plastically, and it is determined by the stress corresponding to the intersection of the stress strain curve and a line parallel to the elastic line offset by a strain of 0.2%. Tensile strength and ultimate tensile strength. It is the maximum load divided by original cross-sectional area, and the percent elongation is given by final length minus initial length divided by initial length, and percent reduction in area is given by final area minus initial area divided by initial area. And we already talked about true stress, true strain. Then ductility is the strain at failure. So if it is more than 5%, then your material will be ductile and it will be having well defined yield point. And if it is brittle, then it will be having less than 5% elongation at failure. Okay. Then resilience is the area under the curve up to yield point. And after that, if you are taking up to fracture point, then it will be toughness. So area under the curve. And impact testing, your strain rate will be very high. So here your materials that show good impact strength are basically metals, and composites and polymers are optimum, and lower will be for the ceramics because there is low plastic deformation possible in them. Then we went through hardness, how to measure hardness, and it's a simple and inexpensive test, and it can also give you idea about other properties such as tensile strength and fatigue strength. Okay, and these were various type of hardness test. Okay, Vickers, Brinell and Rockwell hardness test. Then creep test. In this case, permanent deformation under constant load over a period of time, and it is dependent on temperature. Temperature is also kept constant. There are 3 stages: primary, secondary and tertiary stage. And with temperature and increasing stress, this curve will shift to upwards and to shorter time. Then damping. Okay, that's it from my side. Thank you. Okay, I'll be closing. If you have any query, you can ask. Okay, so I'll be closing the meeting then. Okay.